Now we take a polynomial. In this case, it's a polynomial of order 2, and we want to find the derivative of this. So a polynomial of order 2 is something of the form f of x equals ax squared plus bx plus c, right? And I can change my a. You can see how that affects the polynomial. I can change my b. It also affects the polynomial, and I can change my c. It also affects my polynomial. So if we want to find the derivative of this, we can use the definition. So let's see how to do this. So first of all, we look at f of x naught plus h, like this. This is 1 point on the graph. Then we take, given by x naught and h, and then we take the function value at f of x naught. We divide by the difference in x value h here. And since we know that the function is of this form, we can write everything out in terms of just what we have here. So a x naught plus h squared, right, because there's an x squared here. B x naught plus h, because there's a bx here, plus c, and then minus the same thing, only with x naught instead of x naught plus h. Now we can collect everything that's multiplied by an a here. Oh, wrong. We can expand this parenthesis here, and then we get a times x naught squared plus h squared plus 2x naught h, right? This is what we do if we expand this this square. Then we can multiply the b into the parenthesis, so bx naught plus bh. Then there's a plus c, and then we can multiply the minus into the parenthesis, and then we get minus ax squared, x naught squared, minus bx naught minus c. And if you notice, then there's a b here, a c here, and a c here. There's a bx naught here, and a bx naught here. There's an ax naught squared here, and there's also an ax naught squared here. So all of these cancel. What are we left with? We are left with an a times h squared and a times 2x naught h. That's what we have here. And then there's this bh left. Everything divided by h. All of these manipulations, of course, work as long as h is non-zero. But now we can take this fraction and we can reduce it, because there are h's on top at all the factors. So let's just reduce them. So h squared becomes h, 2ax naught h becomes 2ax naught, and bh just becomes b. So this is what we're left with after canceling out the h's. And this number here, which depends on x naught and on h, this is something that is also defined for h equal to 0, right? And what happens when h tends to 0? This disappears, right? Whatever a is multiplied by something that becomes smaller and smaller becomes as small as we like, right? So we're just left with these two terms. So in other words, the derivative of f of x at the point x naught is 2a x naught plus b. So the c doesn't influence the derivative, which makes a lot of sense, right? Because if you take the derivative of a function, it's just the slope of the tangent that matters, and since c just determines the height of where we write this, it doesn't affect the slope, right? So the derivative, the derivative is this function here. So c I can change without affecting anything else. B affects the polynomial and the line, but not the slope of this line, and a affects also the slope of the derivative, right? We will later on see that the slope of the derivative, so the derivative of the derivative, corresponds to acceleration.